And the topic today that we're going to be covering is SOLIDWORKS Plastics. So for those of you making plastic injection molded parts, you're in the right place, right? It's always good to know. So just real quick, about SOLIDWORKS and about simulation and all that jazz. Like, we have structural simulation, we have flow simulation, we have plastic simulation. All three of these have their pluses and minuses. But really, the thing about plastic simulation, or the thing about plastics that I like the most, is that it's the one simulation tool that it's like directly correlated to like manufacturing costs. The other ones are just simulations for fun, right? I don't want everyone to hear me say that, but really, plastic simulation is a simulation that helps us design things better, and it's directly associated with manufacturing costs. So with that in mind, we're going to take a look at SOLIDWORKS Plastics and see how it can change maybe our design process, our simulation process, the way we improve things, the initial investment, maybe on like a mold or a design, how we can justify that investment, and then furthermore, not only justify the investment, but then expand on that investment if necessary, and justify those improvements, say to the mold or to use a different tooler and so on. So the four topics we're going to cover today is save time. We're going to talk about manufacturing data, why it's important, reduce visual effects, and our quality control. So generally speaking, when we talk about plastic injection molding, right, there are there's some standard information in there, right? I guess it's that early on, and that's kind of what this graph is showing, that early on in the manufacturing phase, let's say in the part design phase, making subtle changes to draft or ejection pin locations or just the overall shape of the part is really easy, and it doesn't cost hardly any money, right? So the idea is that you can make a whole lot of changes without impacting the financial, bottom line of that project that you're working on. But then as this project kind of transitions through the manufacturing process and goes from design to approval, and then goes to tooling, and then goes to, injection molding, then as we move down that line, the cost to change drastically changes, right? So a small change on the mold is extremely expensive in comparison to like a small change on the part design, right? So when you have to change the mold somehow, right, things get expensive. So with this in mind, what we're going to do is tackle how SOLIDWORKS Plastics can help you in that part design mold, or the part design mode, right? That validation section, allow you to make all the necessary changes right off the bat, reduce a lot of those negative externalities, and do that all up front so that you're not stuck with those high bills, right, later on in the manufacturing process. So just like anything in SOLIDWORKS, plastic has multiple tiers. We have the standard tier, professional tier, and plastics tier, or plastics premium tier rather. And we are going today to be concentrating just on plastic standard, because there's a whole lot of bang for the buck there. Like really, there's a ton of ways to save money with just even the standard tool. So of course, if you guys have questions about the professional and premium tool, we can help you out with those. But for today's sake, we're just going to be looking at the plastic standard. So let's get everyone on an even keel with what the injection molding process is, right? This is like a really light mock-up of the machine. So you have essentially 4 stages. The first stage in an injection molding machine is that you pour plastic into a hopper. Usually there's some sort of dryer, either like an incandescent dryer or something to remove oil if it's a plastic that absorbs oil, and it goes down into the barrel, which would be like this section right here. Maybe you can see my mouse, maybe you can't. So it goes from the hopper to the barrel, then it gets heated into a liquid, which flows like liquid honey down through the end of the nozzle, into the sprue, into the runner, into the cavity. And this is kind of just a blown up version of that sprue runner cavity kind of thing. And it wants to flow, I guess, in this cavity, because it's being forced in, right? And it's like it's flowing like liquid honey. Think about honey in the refrigerator, how difficult it is to get that out, and then honey that you put in the microwave for a minute, and then how nice it flows. That's essentially how the plastic is moving through the machine and then into your part. And then after it fills the cavity, there's a pack stage, which its sole purpose is to make sure there's uniform density across the part, that the plastic part is solid and continuous, right? And then it's got to cool for a second, so the mold will stay closed while it's cooling. And this is usually the longer time of the three between fill and pack. And then the mold opens up on the parting surface, parting line, and then the part ejects. So that's my quick 101 on injection molding, just so we're all on the same keel. That's, if that was a repeat for you, okay. but yeah, for anyone new to injection molding, that's the general workflow there. So talking about saving time, communication is key with any project, right? And think about the last project you did, right? The last project you did might be something as simple as like a single cavity mold or a multi-cavity mold, like whatever. Think about the last project you did and how many times you had to communicate with either the manufacturer or or some sort of contractor to get this thing made, whether it was like a goof on a drawing or, hey, can we change the draft in this location? Like, it's a huge time suck. And while everyone's waiting to get responses and returns, like return emails or return replies or whatever it might be, nothing's being done on your part. So with plastics, we can alleviate some of that communication inconvenience and be more prepared to have this conversation earlier on, I suppose, with the contract manufacturer. So we can look at a design, hypothesize some gate locations, and then change the design or the gate location based off of just a simulation, which is really where plastic fits in. And then if you make a change, or if you need an improvement, or you need to understand how much this part costs, to manufacture before we even go get a quote, you could have a pretty good idea of that, right? Now we have this really great return on investment YouTube video for plastics, and it kind of just shows you just how easy it is to recoup or to earn back, right? What plastics cost you, and most times with lots of customers, it's far less than a year. And if you watch that video there, you'll get a good idea about what that is. So let me ask you this now, right? It's like anything else in life. Hey, let's go order some food. Hey, what about a steak? I'm gonna get a steak. And you go to a menu, you look at a steak, and you're like, oh, I'm hungry today, and I want something good. I'm gonna treat myself. Maybe I finished a project. Maybe I passed a certification. Whatever, right? I'm gonna eat something good. I'm looking at these steaks. What am I looking at when I'm buying a steak, right? I'm thinking about how I'm gonna cook it, I guess. I'm looking at the menu and looking at the prices and seeing like, well, why is that one $60 and why is that one $80? And maybe that's a cowboy steak. Maybe that's I don't know. I'm not a steak expert by any means, but like an aged ribeye or something, and then you're thinking like, okay, what do I want on top of the steak? It's like, and if it was closer to noon right now, I might be getting hungry. But then we think like mushrooms and all these additives. So it's like, okay, you're spending money and you're buying food, right? And you're making a decision based off of the stuff right? That's good. So how is that any different when we're manufacturing something? It really isn't, if you think about it. Instead of thinking, oh, I'm going to go buy a steak, it's like, no, I'm going to go get my, and like a lot of the times when I get parts, I'm spending my own money. So it's the same concept, right? So I'm spending my own money on steak, or I'm spending my own money on getting something made. So if you apply that same logic to your manufactured parts, well, instead of how it's cooked, what's the cycle time? And why is the cycle time important to me? Well, how many parts can you make an hour? How much does it cost for that machine to run an hour, right? Furthermore, what type of machine does it have to run on, right? Instead of the grade of steak, what grade of machine? So you could imagine that like a 40-ton machine would cost significantly less than a 400-ton machine, and so on, right? What's the quality like, right? So with plastics, we can look at the quality ahead of time, right? To look at the weld lines, sink marks, and I have some great examples of what these look like. But do you need someone at the machine, operating the machine, or is it going to run 24/7, right? Or do you need an operator there to pull the parts out and inspect them and put them in a go no go pile? You shouldn't have to do that. But the reality is, if you're not using plastics and you run in that scenario, that's the only way to do it, and it's too late, right? And then it's like, well, what if we use different materials? Let's hypothesize what those different materials could be. Well, you're not going to make a mold for each material. That's, expensive. Why not just virtually test it inside of SOLIDWORKS Plastics? There you go. And then the sides, right? Comparing the sides to side effects, or sides, side effects. Whew. Let's see, we have sink marks, weld lines, flow patterns, and then extras. And there's just other things, other visible things that you can get, or visual indicators that you can get from plastics that are certainly helpful too. So, applying logic of, grabbing a steak versus, or ordering a steak versus ordering a part to be manufactured certainly has some tangibility. Why don't we just break it down and think that way, right? Now, if you stuck 11 engineers in one room and one chef in the same room, right? The 11 engineers wouldn't draw any tangibility to ordering a steak, right? I suppose they would just say, well, you need plastics because of these technical information, right? But then the reality is, it's just like any other decision that we make, which is maybe what the chef might bring in to the menu. So I always say, diversity is innovation, and if we can get some more folks thinking about like manufacturing in a different way, then we're really making progress. And so maybe this is just a little exercise to make you think differently. So, we, at the end of the day, we want to reduce the costly manufacturing, right? So, and typically what happens in injection molding is there's, you decide to manufacture something and you make it, and then there's some sort of side effect. And then these side effects have to be fixed. And these fixes cost money. And so what do these side effects look like? A weld line in a transparent part, right? Looks like a hair through this plastic piece of glass, and it's worthless. Right? That's when they make lenses. The lenses are so big and they cut them down to the shape of a sunglass. But the actual lenses before the sunglass shape is made, they're much larger, so that all the imperfections kind of move outside. Shrink. If two components are meant to snap together and they don't, it's a dollar store product now, right? Think about that last broom you saw at the dollar store for $4, let's just say. And it had a dustpan. You're thinking like, well, why is that $1 or $4, whatever? It's because the dustpan doesn't snap onto the pole, right? The dustpan was oversized, and it kind of fits on there, but then it just slides to the bottom and it falls off, right? By the way, a dollar store is a great place to go to look for not defective parts, just parts that have manufacturing difficulties. Make sense? Gate blemishes, sink marks. Sink marks are ugly. How much texture you need? How much sink mark do you have? I don't know, right? But those are the questions that we should ask ourselves when we're making our parts and designing them and deciding to manufacture them. And then air bubbles and venting. So financial roadblocks are also something that's difficult to navigate when you're talking either to a customer who's injection molding parts, or you're talking to management about injection molding parts, or maybe your manager per se. So we talked about cycle time just real quickly, like right in the beginning, that cycle time is a, it's one of the key indicators for us to help manage or to help improve how we might push our projects, through down the pipeline. And so why is cycle time important? And then why is all this other data important when we look at SOLIDWORKS Plastics? So when we look at cycle time, it's going to tell us a couple of things, right? It's going to tell us, when we look at SOLIDWORKS Plastics per se, it's going to tell us a couple of things. It's going to tell us how long it takes to fill, how long it'll take to pack, how long it'll take to cool, right? And so those are three good indicators about how long the actual filling process is, the packing process, and the cooling process. So that gives us what's going on inside the machine. And then we add one more factor to that, which is how long it takes the machine to open and close. Now, with older machines, that could be, 6 to 8 seconds. On newer machines, it could be 2 to 4 seconds, right? So, your cycle time tells you essentially how many parts you can run a minute, or therefore how many parts you can run an hour. And so why do we need to know that information? Well, different machines have different hourly rates. So a 60-ton machine, just generally speaking, like here in California, is about $45 an hour. A 90-ton machine is about $65 an hour. And then like a 250-ton press is like $180 an hour. So then we have that talk and say, well, knowing the size of the part that we have now, what's our target goal? What's our target piece price per part, right? What do we want this part to come in at so that everyone up the stream can make 50% or 70% or whatever? And so maybe you say that's like a quarter, right? Now let's just say we run this, we figure out the cycle time, right? And then we figure out that, this, you can run a part a minute, right? One cycle a minute. And at a 60-ton machine at $45 an hour, that means you get 45 parts that are $1.20 a piece, right? But it's not going to get us to a quarter, right? So then what does that do for us? Like if our target goal is a quarter and they're costing $1.20 now, how many cavities do we have to make this, this part come in at an effective price? A 5-cavity mold, right? So that would justify our financial decision to say, hey, let's go from 2 to 4, instead of 4, let's go to 6, or instead of 4, let's go to 8, so we can get these piece prices down below, below quarter. And so that justification is also kind of worked through with SOLIDWORKS Plastics. Like, these are all the decisions you can make with it, right? So in addition, one of the things that I feel like is also kind of like can be in like a weird scenario, and it's also just a peace of mind. When you go rent a car, like let's think about the last time we rented a car. When you go rent a car, you just say, I want that one. You don't care about the price, and you just take it off the lot and on your way? Probably not, right? So you're probably thinking like, okay, well, I want to get a deal. I want it to be budgeted. So, you go look online, you find the best rate, you spend 15 minutes, you save $100 maybe, and then you go rent, a mid-sized car for $33 a day, right? So you do all that effort just for a rental car. Why don't you do that same effort for machine selection? So with SOLIDWORKS Plastics, what we can also do is figure out, what the tonnage essentially is required, what ton machine is required to keep the mold halves together. Now remember, as we're pushing plastic into the mold, that plastic's trying to force that mold open. So some of the forces equal 0, if you will, right? So we're taking this rod, ramming plastic into this cavity, and even if that mold moves just like a thousandth of an inch or a half a thousandth of an inch, you're going to get flash. You're going to get something that you don't want. So the machine really has to make sure that there is no movement, right, between the A side and the B side of the mold. So we can calculate this value based off how many cavities you have, your gate and runner and sprue locations and diameters. We can figure this out, right? And what that means for you is that ahead of time what machine or what type of machine, or rather what ton machine you need to run your cavity, to run your mold. So now why is this important? Well, besides the hourly rates, you can suggest to your mold maker or to your manufacturer that, hey, we want this run on a 60-ton machine because we don't want to pay $90 an hour. Right? Well, maybe they don't have any 60-ton machines open, so they're just going to throw you on the 90. They're not going to give you a discount. Right? Oh, I need my parts done in 2 weeks. Okay, well, if you want it done in 2 weeks, it costs this much more. Why? Because they're running on a 120 machine or a 110 or a 90 or 60 or whatever. It's not running on that 40. So this is the same concept of renting a car, right? You don't go rent when you're renting a car, you take the time to figure out which car is the best bang for the buck for your trip, right? If you have 7 people, hey, you got to buy a big car, right? But if you have 3 people, why rent a Suburban? Right, for 3 people, it's got 8 seats, 9 seats, or something crazy. So why are you paying for a Suburban when a mid-sized car will do? Why are you paying for a 120-ton machine when a 45-ton machine will do? Right? Easy way, easy cost savings, guaranteed. Okay, moving on. What are some of the negative externalities? Right? These are the things that happen down the road when we don't do a plastic simulation. Right? So we have an operator, a dedicated operator that not just sits there, that not just like rotates to different machines, but then also sits there at your machine and inspects every part that comes out, right? And why is this necessary? Because there are problems with your mold, right? Because there are problems with the plastic flow. And so because of the inconsistencies, you now have to pay for an operator to sit at your machine in addition to the hourly rate to inspect your parts and trim the gates. Bummer, right? Negative externality. Maybe not only that's required, but then you also have to pay for jigs and fixtures, right? To hold those parts flat, to keep them the way they were designed, to keep them straight or flat or whatever it might be, because like maybe your gate location is not optimized, right? So the other thing too is like repeatability is a huge issue a lot of the times. Like, hey, the mold runs fine until it gets 2 o'clock in the afternoon and it gets hot in California. Or hey, it runs good until it's, you know, midsummer and the humidity is 110%, right? And it's just, there's just so much moisture in the air. We can't keep the moisture out. So all of these things are factors that we could mitigate, in addition to, you know, the quality, the weld lines, the you know, looking at the flow, selecting the right machine, so on and so forth. And it's all done with plastics, right? So now we're just going to talk about what plastics looks like and the things you can do with it. So that's my pitch, my spiel on all the different ways that you can think about plastics, I suppose, SOLIDWORKS Plastics. And you know, selecting a gate location. Generally speaking, you want a gate from thick to thin, right? And if there's a rib behind it, that makes it better. It allows your plastic to move and flow easier. But we can add gate locations. This is what SOLIDWORKS Plastics looks like. Keep in mind, it's built into the SOLIDWORKS interface. Here is what sink marks look like, so we can take a look at those negative externalities before you know, the part gets actually made, and then you're just stuck with kind of what you got. One thing I like to tell about sinks is that you know, when you do have sink, it's good to know how much and where, right? Because this tells you how much texture you need to apply to your part so that no one can see your sink, right? If you look at the dashes of vehicles nowadays, this is a really good example of all the texture they put on there. Because that dashboard is like so big, it's naturally just going to have flaws everywhere. But if we know like where those flaws are going to be, we can pull some out. And if we know by how much those flaws are, then we can hide them. Just like you texture a wall, you know, in your room with the orange peel, you texture a part to hide its imperfections. Another kind of useful tip, right? Uniform wall thickness with ribs at 60% of the width. Just some fun facts. These are the things we need to know when we're manufacturing plastic injection molded parts. Another example of what happens to a rib if it isn't designed correctly, right? You have these ribs with varying draft, and then where the draft is super heavy, the part, you know, remains hot, and where it remains hot, you're just going to have more sink, right? So just a good visual about some of the things you can see in your design. It's, you know, plastics is going to tell you, hey, look, these regions are hotter than they should be, and therefore, what are the negative externalities associated with that? Well, I don't know, Adam. What do you think they are? When you just think to yourself, right? Like, okay, I'm expecting this, this, and this to happen at these locations. This is giving us ammo to critically think about how we've designed the part, how it's going to be manufactured, and then to take that information and judge it, and then to inspect it, and then to make improvements. Here's an example of a flow line that could have been mitigated with SOLIDWORKS Plastics, right? Again, these are like, they look like scratches, but they're not. And if it's on a clear part, they look like a hair inside of the transparent part, but it's not. And you know, the funny thing about transparent parts, we can maybe take it for granted, but transparent parts come out foggy. So when they come out of the machinery, they're not entirely cool. Most plastics come out foggy, and so you can't even see through this fog until the part cools after 5 or 10 minutes. So inspecting for weld lines would be an additional process. So it would require another operator to then look at each one of these parts, right, and then toss out the ones that are no good and keep the ones that are good. So, you know, it's like one thing after another, and everything stacks, and everything gets exponentially more expensive, you know, as the manufacturing process continues down the road. So this is a good one. This is easily seen in transparent parts, but this is also measured with just mass or grams. So in this example on the left-hand side, this is like a handle, and the handle has this giant void, right? And the void where there's essentially an air pocket in there, right? And then so how much you test for air pockets? Well, in SOLIDWORKS, we know the mass of this thing. So if we weigh this part here on the left and compare it to the part on the right, then we're going to see a discrepancy in how many grams of plastic are in there. And then we can say, oh, that one's junk, right? And toss it out, throw it away. Again, these are things that we can see with SOLIDWORKS Plastics to mitigate these negative externalities. Man, I keep on knocking my key off my keyboard. It's just fantastic. Okay, so weld lines also appear when there's some sort of flow around a hole. So this is like a through hole, and where the flow, you can imagine if my face represents like where that hole might be, right? Then or think about just water moving around like a rock, right? It hits the rock, diverts left and right, and then comes back behind it and meets. Like in a stream, there's all those eddies and all that extra air and all that kind of movement that's going on right behind it. That's actually kind of like right where fish like to chill. If you're stream fishing, toss your lure back there and catch some dinner. But beyond that, all those little eddies, like that same sort of concept applies to plastic. So when the plastic flows around like a pole or an opening and then it meets back up, you get all this like jumbled, disassociated, not completely mixed flow fronts that are at slightly different temperatures that then cause these micro dislocations or micro cracks in the design, which is essentially either one, visually not satisfying, and then two, structurally weakened in that location. Short shots is another great one for plastics, right? How do you know if your part's going to fill, or how much pressure is it going to take, or what's the shot size, right? You can answer all these questions to make sure that we don't get short shots and waste material. Too thick or too thin, right? Some parts are just designed poorly, and no matter how hard you push the plastic in, it'll never fill all the way. That would be a bad mistake. That would be like a redo of the mold mistake, right? Reburn all the cavities. What happens here, right? This is what happens when like venting. There's problems with venting. So this is a little pocket of. So what happened here is that there was a pocket of air which reacted with the plastic and then burned, like the oxygen, and then heat, combust, burn, charred, result. Yeah, that's it in a nutshell. Warping is also a big one, although warping isn't quite in the SOLIDWORKS standard bucket. These are just some other things to be aware of, some other things to think about. It turns out that injection molding flat parts is actually pretty difficult. There's a lot of internal stresses built up, and so we would want to know what that looks like. And in fact, we can solve for this, right? We can get a pretty good idea about how a part's going to warp and what we can do to mitigate that and heat the mold differently and so on. So talk about what we learned today, right? We'll keep this conversation more manufacturing oriented, less software oriented, and just how that SOLIDWORKS Plastics can improve your day-to-day workflow for essentially not a whole lot of investment. But what we learned, we can save time, increase confidence level with plastics. We can make financial decisions before it's too late, what machine to use, how many cavities to use. I suppose where we're going to, whether it might be in China or US or somewhere else, right? Depending on how many cavities there are and the cost, you could help justify that. Spending money on the right upgrades. So a lot of the times, we look at, recommendations from injection molders, and they might say, well, we need this and that and this and this. And be like, well, no, I really want to have 6 cavities on this mold, so we need to make sure we do that first, and then we can do some upgrades to hot runner systems after the fact. Or maybe just use like the submarine gates instead of a hot runner, right? So that it ejects automatically and splits the gate for us. So if you are on a budget, what is the right area to spend the money on? Well, that all depends on how your business plan for your product, and then we gain a really good understanding about what the manufacturing process looks like and how much it might cost us, just based off of the SOLIDWORKS Plastics standard tool. With all the examples that we talked about, like all the negatives of injection molding, if we know where there's going to be a weld line, if we know that there's going to be an air pocket, if we know that sink is going to be by X how much, then and we know that beforehand, then we can make all these decisions after the fact to we can make all these decisions before we get the mold made, so that after the fact we don't have to do these, right? Or after the fact we don't have to have an operator stand at the machine, or after the fact we don't have to pay for, you know, jigs and fixtures, right? And then I feel like globally, or like really the picture I tried to paint here was just the process of injection molding, right? And that it's not, I mean, even though like we justify it by renting a car, or we justify it by ordering a steak, there are a lot of layers to injection molding, but really using SolidWorks Plastics allows you and your team to make responsible decisions up front, and then, you know, essentially not be careless with project funds, right? It's also a really great safety net for engineers, right? I'm confident because I'm confident saying, here's what I want. I'm an engineer. Here's what I want. I don't injection mold all the time, but I run a simulation, so I know what I want. Here's what I want, and you can pass that information along. Now, generally speaking, we would rely on maybe others to tell us what, you know, hey, how does my part look? What should I do? And maybe you have a really good contract manufacturer, right? And I have one of those, and we're actually friends, right? When I get my injection molded parts made, and it feels like that when I show up. But not everyone is going to be optimizing your part for you, right? They're only optimizing the part so that they can make it easier, or they can make it faster, right? Especially the case in China, right? So those workers get paid per piece. If they can run your mold 50% faster, right, and dish out these parts that look okay, but that later on you find don't perform okay, they're happy because they got 8 hours of work done in 4, or 8 hours of work done in 6. So, everyone's just covering their own end of the stick, right? It's just like, hey, here's what I have to do to make money on this part. But if you're not running a SolidWorks simulation, right, chances are you're missing on opportunities to save yourself some money, right? For an injection molder, it might be like, oh yeah, if we do this, we can save 10 minutes on the cycle time. Okay, that saves you some money, but that saves him even more money. What about the ones that just save you money? Right? That's why we need plastics. So here I have a challenge for you. It's like, think of the last difficult injection mold project or plastic part design project that you did last, right? And that you did in the past. And think about all those negative externalities that might have been associated with that project and how tough it was. Could you have taken just one step out of that whole entire process and simplified it with plastics? Could you have saved, just a little bit of money, right, with a rework for SolidWorks Plastic? Like, was there something you could have done just marginally different to improve how that project went from start to finish? Or knowing what you know now, what would you change about one of those parts that you've made, or one of the molds you decided to purchase? And the reality is, and we can share this in chat too, if we like. Does anyone have a good example, I guess, of a rework that they did recently? So a rework that maybe cost a couple grand, or even worse than that, like the part didn't mold, or it didn't shoot, or didn't, something didn't go on. Like, we'll go ahead and I'll kind of just wait for a second. But I think the last thing that I did, that I helped a customer on, it was a relatively large order. It was a very expensive mold. The mold was one mold but 2 different parts, so you could swap out like an inner cavity. There was like an A and a B cavity, and you can swap one out, and it would make the opposite part. So the first batch gets run, right? And it's a brand new product. Keep in mind, it's a brand new product. Big company wants this part run. 2 pallets get sent out to the big company, right? They show up. They run their tests. They refuse to pay the contract manufacturer for the parts, saying that he's done something wrong. Oh, really? Like $30,000 in parts. Hey, we're not going to pay you because we're the big dogs and you've done something wrong. Later to find out that when I stepped in, I ran the plastic injection molding software, figured out all the issues, gave that to our contract manufacturer, which in turn gave that to the big dog. And they were like, oh yeah, we made mistakes. Oops, here's your 30 grand. True story. Mike Monson from Montel can vouch for that. So does anyone have any examples of maybe how much it costs for them to rework their last mold? Or if they want to share, you can just type it in chat. So the reality is, oops, wrong way, is if the answer is, greater or equal to 5,000, then you could have justified paying for SolidWorks right now, SolidWorks Plastics, standard at this very moment. And you think $5 grand in one part, that's like so easy to do, right? Like let's literally, it's like one little thing that goes wrong cost you $5 grand. Okay, let's entertain some ideas. Like obviously there's the whole tooling thing. Oh, we need to make a change. Okay, send it back to the manufacturer. We'll go make a change, add another cavity, $5,000 bill. No problem. That one's easy, right? It's easy to say like, oh, hey, there's this, $5,000 change on the mold. Sure. But what about the other things that are maybe like less tangible? Like, oh, we put this in the machine and you lost 3 weeks of production time. Now you're put back into the calendar and you have to wait 2 weeks because that machine's filled by someone else's order. That's a bunch of money, right? That is a bunch of product, a bunch of money that could have gone, essentially in your company's pockets, but now is gone forever. You've lost that opportunity. That time is gone. You can't make up that time. Whatever it was, it was, and then now we've moved on. Right, so you got to think about those intangibles, I suppose, that are just lost business opportunities. So my name's Adam Hughes. This was my spiel on SolidWorks Plastics. Maybe a different approach than what you've seen in the past, but it's all about manufacturing. Now, I have an injection molding machine in my garage, and I have a CNC machine in my garage. I machine my own molds. I cut my own parts. I make my own plastic parts quite frequently. And nothing's like ultra straightforward, and there's a lot of things going on. But really, I couldn't do what I do. It's just like a one-man shop without plastics, without SolidWorks CAM, right? Like those tools are my bread and butter, and I like to think, one, they keep me safe so I don't screw anything up, and then two, they get me in like that 95% range, right where I need to be to just dial in my machines so that I make the parts that I want to make. So, oops, that's what we got for today. My name's Adam Hughes. Thanks for watching.